welcome to Engineers Workshop, coming to you live from Phoenix, Arizona on a service call. I figured I would send out a video showing some engineering I got to do for my son Brennan on a project that he had. So his channel is called The Facility. Now, I got to caution you, he's pretty blunt, so his channel is not quite as kid-friendly as mine, but who am I to argue? He has 1.2K subscribers, and I have under 600, so he's twice as popular as me for the moment. He's a brand new engineer, and I'm an old, crotchety 30-year engineer, so we've got the same path ahead of us. So a few years back, one of his projects that he decided to do was a custom motorcycle of his own design. And he's not the type to power these projects with conventional powertrains. So he was going to use a Hatz diesel, two-cylinder little industrial diesel engine to power this bike. And we scoured the eBay pages, and we bought a Hatz diesel. Here it is as we were picking it up from a Fastenal freight location, and I cracked it open and sent him some pictures of it before we even opened it up out of the box. Painted in its yellowish and blackish, who knows what colors, but right out of the piece of equipment that it was powering. Beautifully engineered. Popped the valve cover off, and you can see the lash adjusters over on the left, and just the deformed thread fasteners to prevent vibration loosening. And the model engine that he chose was a 2G40H. Now there it is in all its glory, ready for a new home. So the engine is approximately a 17 kilowatt or 20 horsepower engine. It has right at 1 liter displacement, and its original life was in one of these devices, a trench roller or roller compactor. Now, the engines are well built, and they're pretty expensive. If you look on eBay, here's a like brand new one for $5,000. Here's a $2,200 one. Here's a $1,100 one. He didn't have that kind of money to spend. He managed to find one that was about, $200. If I remember correctly, it said runs but smokes. So, how bad could that be? And here's what he's putting it in. He started to rough out a design for a motorcycle using this engine. And the engine is going to be driving the bike through a Honda Goldwing transmission, and the reason he chose the Goldwing transmission was because it had a reverse gear. So you want to obviously have your motorcycle capable of going in reverse. The engine had a couple of problems with it, very obvious ones. We actually started the thing, and we had it out in front of the barn. We got fuel to it. We powered it up. I think it took a 24 volt. We had to put 2 batteries in series to crank it, and it has a Bosch starter. And this thing fired right up and ran, but it just clattered to the heavens and was pouring out smoke. And the first thing I thought was, good golly, how long was this thing running like this? It was obvious that the thing had some kind of a problem. Actually, there were 2 problems. So we had to come up with some solutions that didn't break the budget. Parts are available, but everything is extremely expensive for this engine. So he proceeded to take it apart. And the first issue we ran into was the flywheel. And the flywheel has a tapered bore. It's a pretty steep taper. It's a 1 in 5 taper. And I don't have any pictures of this, but this surface was all galled up, and it was apparent that the flywheel was loose and was run loose at one point. it wasn't loose when when we took it off, but for that surface to be damaged like that, it was clattering for some time. And this is a cast aluminum component, and this groove here on the OD is actually where the ring gear mounts. I didn't model that. But we had to come up with a way to repair this bore. Actually, there's a key also in the bore that is indexed to the ring gear for timing purposes. And what I decided to do was to machine out the original bore and put a steel hub in its place. The complications arose when you looked at the cross section of this, because this was, like I said, this was a casting, and there were no like 90-degree surfaces to it. So you had the back surface, which didn't register against anything. It was all against the taper. And then this one had an angle to it, and all of the fin side also had an angle. So we had to come up with some square, rectangular right angle bores and counter bores to locate a steel hub. And the hub had to start here and end here, so that the ring gear would be positioned and the flywheel would be positioned in the housing. So we ended up sectioning the flywheel, and we put a counter bore in the back and a pilot bore through the center, and then a ring of bolt holes, and we turn off the section. And this is what we removed from the original flywheel. And it kind of landed nicely in with the fins. Every other fin came fairly far into the interior of the flywheel, and so we had to have a spot face on the front surfaces of the flywheel. And then these are all for 3/8 fasteners, and then they bolted into the flange of the steel hub. And this was a close-fitting pilot, and this bore was actually just clearance. So this was a challenging part to model and get everything accurate, but the results of having the modified flywheel assembly bolt into the same location depended on getting everything modeled accurately. And so the final assembly looked like this. We had a ring of 3/8 cap screws, and I made these fine thread, and we had a hub. And the hub was a pretty simple part, made of 4140 pre-heat treated material, which was 27 to 32 Rockwell. Now, the one thing that the fab shop deviated from, if you look at the keyway runs parallel to the bore, and it's a Woodruff type key, and I don't think they machined that taper. I think they ran the keyway straight, which no big deal, as long as it traps the key. It's deeper at one end than the other. But that's our flywheel assembly, and I would say call that a very elegant repair. I think that there's no reason engineering wise that it won't work. Everything that we did matched the original tapers, the original diameters. The pilot was a close fit. The ring of bolt holes out at the perimeter was far enough away from the hub to transmit the torque of the engine without any slippage. And the mass of this steel, this thing ended up weighing maybe 5 pounds, so it added some mass to the existing flywheel, which is always good for a diesel. And there's the print of the flywheel and the modifications we had to make. Let me show you what the actual parts look like, and then we'll talk about the other issue with the engine, which was the connecting rod and connecting rod journal. If you look at the cross section of the flywheel assembly with the new hub, and you overlay the original configuration of the flywheel, you can see that the original surfaces come back to the same point, and the face of the new flywheel hub ends at the same point as the original casting. This area in the back is just clearance. There's nothing that we're interfering with by having that extra flange sticking into that area. So we used it because I wanted to get that bolt circle as big as possible to transmit the torque from the crankshaft to the aluminum without putting these bolts into shear. They're going to be clamping and transmitting the load without side loading the bolts. If you look at the connection from torque converter to the crank, well, let's look at it this way. If you look at the connection of a flex plate to the crankshaft, you've got fine thread bolts. You've got usually 6 or 8 of them, and they're closely located relative to the center line of the crank. Yet out on the perimeter of the flex plate, where it connects to the torque converter, it's usually like 3 bolts, because you've got so much more of a moment arm out to those fasteners. They don't see as much side load. So same goes here. I wanted this bolt circle to be as far apart as possible because it transmits the same load without as many or as big a fastener.
So here's our actual flywheel from the Hatz diesel. Flywheel assembly, I should call it. And I have it assembled, but I'm going to go ahead and take these out. So we used 3/8/16 fasteners. And if you torque a 3/8/16 fastener to 75% of yield, each one is going to give you about 6,500 pounds of clamping force. So if you do the math on this bolt circle, you take 6,500 pounds times 8, so about 50,000 pounds. And if you take the radius of the circle, which I don't know off the top of my head, and you take the coefficient of friction, and the conservative estimate of coefficient of friction is 0.1, and you figure out how much force it will take along that bolt circle to make this connection slip, you will hopefully find, and I'll put the numbers up on the screen, that this connection has far more torque capacity than the output of the engine. And you really got to look at, for a diesel, the power strokes will make a significant torque input to the system, and then you have 2 full crank revolutions where you're losing speed. So you gain speed within about a quarter of a rotation. You're putting energy in to the crankshaft assembly, and then for the remainder of 2 revolutions, you're taking energy out. So a flywheel is an energy storage device, and you will actually put energy into the flywheel. You'll increase its speed, and then when you take energy out of the flywheel, you decrease its speed. So this thing's been assembled for a while. It's a little bit stuck. Very close. There we go. So we have a reference from the shop to orient the keyway, and the keyway, I can see this, is, if you look at the depth of it at the back of the taper and at the front, you can tell the keyway was cut straight. So they had to make a broach that fit that. that's all as cast surface, so we took a little bit out just to clean this up. And that is a very close fit. I'm pretty sure it's less than a thousandths in actual clearance on the OD. But this back surface ended up being in the exact same place as the original aluminum boss on the back side of this flywheel. There are timing marks here to set the fuel pump for the injection. That's why the keyway had to be oriented correctly. These 4 posts, I don't know what they do. I thought they held a rotating inlet screen, but with the way that the cap screws are buried completely in the standoffs, I'm not sure what that does. Only the Germans know. But I'm sure it had a purpose. There's very little in this engine that I question. The engineering seems to be absolutely fabulous, hence the cost of all the replacement parts and the lengths that I went to not have to buy replacement parts. But these will be torqued in place, and this will forever act as one rotating assembly. So I think that all in all, the re-engineering of this came out extremely well. This bore now, and this is 4140, so this bore is going to be very robust and hold up well to the crank. You can see where there was a little bit of pickup from the aluminum that from that bore on the aluminum that was kind of wallowed out. But if we reorient this, oh, it is heavy. There's your assembly. And those threads have a little bit of a burr that's got to be cleaned up as well. Now, when you look at the connecting rod, I'm going to call this the good rod. That's a factory bearing shell. And take a look at that one. And what do you see? What jumps out at you? What jumps out at me is the thickness of that shell compared to that one. Now, if you look at the bore, .773. .736. That is way, way undersized. So what happened in this engine, if I mentioned it earlier in the video, we started it and it clattered just to the heavens and smoked. So there was obviously something slapping around. We disassembled it, and this rod, there was no bearing shell whatsoever. There were pieces of bearing shell in the sump, but this engine ran long enough to take that much wear on the, cause that much wear on the journal of the crank, and simultaneously to open up the bore of the connecting rod significantly. I mean, I can't even imagine running an engine that sounded like that and not knowing that you're destroying it. But what I did at the Napa shop, and you could just about see it, is so this is the good journal. So this is the 1.771, and this journal 1.735. I told the Napa shop, take this journal down until it cleans up. And let's see, 10, 20, 30. It's about 40 thousandths that they removed to get this journal to clean up. Once we had that dimension, I went to Henrico Tool and Die, my favorite machine shop I've been doing with business with for 30 years. And I bought a piece of, I'm trying to remember if this was oilite or if this was just a bronze. I think it's oilite by the looks of it. I bought a 4-inch long oilite bushing that had enough OD and wall thickness to make this part. And what Henrico Tool did was they saw cut it down either side, and cleaned up those faces, clamped the bushing together, and then machined the OD and the ID to fit the new rod journal. I told them to give me 2 to 3 thousandths crush on the OD of the bushing, and then we put it together in the rod after they parted it off, put the two halves together, and then bored the bushing in place to fit the new journal. I know it's a little sketchy, and we have a rod that was technically not serviceable, but this thing was, I don't know, $400 or $500 for a connecting rod. It was $2,200 for a crank, and so it was either come up with a way to repair it or the engine is junk. And like I mentioned earlier, my son was trying to get a running engine for a lot less money than what these eBay engines are going for. So we have a thick shell. By everything that I see, it should work as long as this does not spin in its bore. And there's a couple of Loctite products that I could probably put in when we assemble it to guarantee that the OD of this doesn't spin. It should survive. I mean, as long the engine ran and didn't really break anything, running without a bearing shell for how long that wore this journal and this bore out to what it was. I think that once this thing goes back together, it's going to survive, even with a non-standard journal in it. So I don't know. What do you think? Leave me a comment. But bother my son on his channel, The Facility, if you want to see this engine go back together and run, because I did the machining on all these parts about 2.5 years ago, and they've been waiting for them ever since. Hope you enjoyed that. Our thoughts and our thought process down this rebuilding of the engine. A couple of non-standard repair jobs, but I think we'll have a workable solution both for the flywheel and for the rod journal. Catch you later next time on Engineer's Workshop.